Reptiles are organisms that we know a little bit about in the modern day environment because they still exist. And they're the first organisms that had a backbone that were able to leave the water and stay out of the water, both in terms of their lifestyle, what they ate, what they did during the day and the evening, but also they were able to stay out of the water when they reproduced. And this was something that the amphibians and the fish weren't able to do. So it was revolutionary to leave the water on a permanent basis. And they evolved a very strategically meaningful and important mechanism for doing this. And that was they created an amniotic egg. It was a structure that allowed them to permanently leave the water and be able to reproduce on land. Now, the amniotic egg has a leathery outer membrane. In chickens, it becomes hard, but in the case of the reptiles, it was a leathery membrane. And that's the outer egg coating. And then inside the egg, the amniotic egg, we have two sacs. One of the sacs holds food and protein, and that's called a yolk. And the other sac holds waste products that are made by the embryo that's inside the rest of the egg. Now, we're familiar with these from chicken eggs. When you do break through the chicken shell, this is the kind of structure they have. But they're different because they don't have a hard calcium carbonate-based outer shell. So this amniotic egg allowed them to reproduce out of the water. Basically, it carries the water environment with them, and that greatly increased their advantages for survival in terms of competing and outcompeting and preying on other organisms. So leaving the water permanently was a fundamental benchmark evolutionary event. Now, the amniotic egg then in the reptiles, once that they left the water, and that took place in the late part of the Pennsylvanian time period. And we'll remember that the Pennsylvanian is called the upper part of the Carboniferous if you are in Europe. So the Carboniferous in Europe is the Mississippian and Pennsylvanian ages within North America. So the amniotic egg is what allowed the three great lineages of the reptiles to leave the water. Now what we want to do is we want to recognize what those three types of reptiles were, because this fundamentally sets the stage for bringing onto the planet the dinosaurs, eventually the mammals, and all the other types of major vertebrates that have ruled both the marine and the terrestrial environment since these time periods in the Middle Paleozoic. So as we can see from this diagram, the skull is an example of the first great lineage of the reptiles, and that's called an anapsid. And the anapsids are distinct because they have an eye socket, but behind this eye socket on the skull, there is no hole, no opening. So that means that in order for them to hear, instead of having an ear like we have, they had to use vibrations that were sent from the ground or the water up through the rest of their bone, their skeletal structure. So the anapsids are the first of the great lineages of the reptiles. And the modern day anapsids, the ones to remember, are the turtles. Now, another attribute of the anapsids is that they have teeth that are what we call non-differentiated. In other words, the teeth through their entire life and the life of one single organism going from a juvenile to an adult, we call that the ontogeny of an individual. So the entire ontogenetic history of the teeth of the anapsids are non-differentiated. In other words, all the teeth are more or less the same. They don't have really distinct structures and sizes. And during the entirety of their lifetime, those teeth are exchanged and redistributed and replaced throughout the history of the organism. So the anapsids are the first great lineage, and modern-day turtles are the example. The second one is what we call synapsids. And you'll see synapsid, it has one skull opening behind the eye socket. So if you go from the eye socket and then backward on the skull, there's only one opening, and hence the word synapsid. The synapsids are the reptile lineage that eventually led to mammals. So this is the lineage of reptiles that we have evolved from ourselves. One of the hallmark characteristics, besides having one hole behind the eye socket, is that these organisms have differentiated teeth. In other words, there are canines like we have, there are front incisors, there are molars in the back. If you forget this, all you have to do is look in the mirror, because humans have evolved from the synapsids. So differentiated teeth, and those teeth are not constantly replaced throughout the ontogenetic history of the individual. Those teeth are only replaced once. And again, if you forget this, just remember from your own history growing up yourself. So the synapsids is the second great lineage. The third great lineage of the reptiles is called the diapsids. And the word "die" is two, and that means that there are two openings in the skull that are behind the eye socket. And another thing really important about the diapsids is that they were the lineage that eventually led to the rise of the dinosaurs and then eventually to the rise of the birds. So this is the other major group of reptiles. And one of their hallmark characteristics, besides having two holes behind the eye socket, is that their teeth, again, as the anapsids are, they're non-differentiated. In other words, there's not a lot of difference between all the teeth. They have more or less the same kind of morphology, but also throughout the ontogenetic history of the individual, all of those teeth are continuously replaced. All right, so now we have our three great lineages, and what we want to think about are what are some of the types of organisms, reptiles, that evolved that represent each of these lineages. We mentioned the turtles was for the anapsids. And most people are familiar with the idea that there's an outer shell and then the turtle's able to retract its head completely within the shell. We're not going to spend a whole lot of time on the turtles. They're fascinating, they're interesting, but they end up being not extremely important for the fossil record in the way that the other two great lineages are, the diapsids and the synapsids. We want to now embrazen in our mind exactly what the differences are between the synapsids and the diapsids, the rise of the dinosaur lineage and the rise of the mammal lineage. So let's look first at our historical lineage. That's the synapsid reptiles. The synapsid reptiles basically had three major types that we want to remember. The first one are called pelechosaurs. And the pelechosaurs were heavy-boned. They had large front limbs, and they actually created organisms that from a distance, and if you didn't think carefully or at least take a course in evolutionary biology, you'd probably think that these things were dinosaurs, looking at them briefly, but they are by no means dinosaurs. These are pelechosaur synapsids, which led eventually to the rise of the mammals. Now, there were many types of pelechosaurs. Some of them were small lizard-like organisms, 50, 60, 70 centimeters in length. But there was another one that rose to the point that was remarkable because A, it became the top predator in the terrestrial environments that it lived in during the Pennsylvanian and at the early part of the Permian. But then it also has a very distinct morphology. It has a series of spines that rises off the back part of the vertebrae. So these spines rose upwards of 1 meter off the back of the pelechosaur. And the pelechosaur had this particular group, it made up 70% of the predators that were living at the early part of the Permian. 70%. That's a huge proportion. In other words, these were the first major terrestrial predators, and they did incredibly well. So the name of the pelechosaur that had the spines that were so prevalent at this time period is called Dimetrodon. And the spines of Dimetrodon rose up approximately 1 meter or so off its back. They were small and slender, and then some of them had cross links on them to even make more surface areas. So the way the spines worked is that they would stretch membranous skin across the spine network, and then the hypothesis is, based on imprints of blood vessels and other things in the bone mass, that they actually fluxed blood through those membranes. And if they had the membranes and their large fin of spines on the back, if they positioned themselves with the sun, they could warm up their blood. All of these organisms were exothermic. They derived the majority of their heat from the environment. But one possibility, though, is also not just heating their blood using the spine framework, but they could also cool it. If they became too hot during the day, they could reposition themselves in the shade, flex the blood through it, and that would also allow heat to be dispersed instead of being acquired. So Dimetrodon was extremely important to us. And some of these even got up to 300 kilos in size. So these are major predatory organisms. They move pretty fast, and they had another hallmark of the organism is they had a very large canine, the incisors that come down on each side of the mouth, and that allowed them to attack quickly, bite into prey, and hold on to it as they ripped it to shreds. Now, another type of organism that we want to identify here is the therapsids. So we went from the synapsid lineage, which came up in the Pennsylvanian, to the first major synapsids that were predators, which were pelechosaurs, and the main one that we identify within them is Dimetrodon. Then the next stage in evolution were the therapsids. And the therapsids were large, wolf-looking reptiles. They had spines that had been evolved to, and scales that had evolved to become very thin and narrow, and eventually hair. So they had an early form of hair that covered the entire body. And hair is really important because hair is very good at trapping air. And trapping air is one of the best mechanisms for insulation. So once they got body heat derived primarily from the environment, then they could trap and keep that body heat with the hair. They also had the large incisors, they had an extended snout, and for all practical purposes, as you can see from this diagram, they looked a lot like a wolf. So the therapsids were the next important evolutionary step, and towards the end of the Permian, the Dimetrodon organisms were replaced and outcompeted and preyed upon by the therapsids. Now the therapsid, again, this is still in the lineage to the mammals, was much larger. It was twice the size. It had an extended, as you can see from this diagram, a much larger set of front legs, and therefore the animal kind of stood with its shorter back legs, upper front legs, and it stood almost like a wheelbarrow upward, and it had extremely large musculature that covered the pectoral areas of the front limbs. And then it also, on top of that, developed extremely large muscles in the jaws. As you can see from this diagram, that the jaw had a muscle attachments that were coming out in the bones that allowed large masses of muscle to attach to it. So these things could really rip and shred, and because of their big, bulky, extremely well-developed musculature in the front, these again were the next version of a very serious predator on the planet. Now, something we want to think about for the lineage of the synapsids is that this group of synapsids called the therapsids, they made it through and survived the greatest meteor impact that we've had so far. This is at the Permian-Triassic boundary, approximately 251 million years before present. 85% of what was living on the planet went extinct at that time, but the therapsids made it through. And again, if you forget about some of these things, just remember, yeah, we are humans, we derive ourselves from the synapsids, therefore we know that the synapsid reptiles were one of the ones that survived the great meteor impact, and we call that the Permian-Triassic boundary meteor impact event. Now let's move to the diapsids, because the next step in the synapsid evolution is to move into mammals, and we're going to be looking at some of those in more detail. But to lay the groundwork, we want to now switch over to the third lineage of the reptiles called the diapsids. And the diapsids are extremely important to us because as they rose in this time period, they developed reptile-like organisms. They were reptile, but they looked like reptiles, and especially some of the reptiles we still have now, and eventually evolved into the true dinosaurs. So the diapsid lineage included a whole series of types of reptiles that first invaded and did very well back in the marine environment. Now remember, the reptile is defined by having an amniotic egg that let them leave the water and move into the terrestrial environment. But indeed, once they got out, they found it was advantageous to get back in. And so the first set of reptiles that evolved all lived in the marine environment, and then some of those again re-emerged from the water, and then they were the ones that evolved into the dinosaurs. And importantly, we're going to see that that lineage then is capped by the end of the dinosaurs, which eventually evolved then into the birds. So each day that you were walking across a set of trees or any place on campus or wherever you are and you hear birds, that's the song of ancient dinosaurs. It's not just simply the song of modern day birds. So the diapsids, the synapsids, and the anapsids. These are the rise of the three great lineages of the reptiles.